Hello and welcome to this online lecture. Today I would like to talk about flutter, what it is, how it arises, why it should be prevented in the design of long-span bridges, how this can be done, and perhaps more importantly, how this can be done economically, that is, at low cost. Concerning the latter, I'm going to focus on a particular device called the eccentric wing flutter stabilizer. Let's start. I like this picture very much. The outrigger boat we see here is light but stable in rough seas, and therefore bears resemblance with the flutter suppressing device I'm going to talk about. But let's first see what flutter actually is. Flutter is a coupled vertical torsional vibration of the bridge deck that occurs when the structure has certain characteristics and the wind blows at a certain speed. A small initial vibration induced by any kind of momentary disturbance, such as a wind gust, does not subside but continues and possibly increases in amplitude even after the initial disturbance has passed. The phasing between the vertical and the torsional components of the vibration is such that flow energy is continuously fed into the system. For sake of illustration, let's assume that this phasing is 90 degrees. When the bridge deck moves vertically and passes through the neutral position, note that the vertical velocity at this point in time is at a maximum. The rotation, alpha, is also at a maximum, and therefore also the lift force on the bridge is at a maximum. This means that the vertical lift force is in phase with the vertical velocity, and this actually at any time during a vibration cycle. A force in phase with velocity, however, corresponds to negative damping, meaning that energy is fed into the system to the effect that the vibration continues with the same amplitude or even increases in amplitude. Flutter is feared because it is a stability phenomenon, comparable to the buckling of a column or a plate. It occurs suddenly and possibly unexpectedly, and when it occurs, little can be done and the consequences can be disastrous. More specifically, flutter is a dynamic aeroelastic stability phenomenon that arises from the interaction of three kinds of forces: the elastic restoring forces and the inertia forces of the structure, and the aerodynamic forces. In the pure form of flutter, no imposed external forces, say from turbulence or vortex shedding, are involved. The time variable aerodynamic forces on the structure are solely induced by the motion of the structure. Indeed, they are modeled as linear functions of the displacements of the structure, which are summarized here in the displacement vector phi. Consequently, the mathematical representation of the dynamic force equilibrium is a homogeneous system of linear equations, here shown in matrix notation, in which the aerodynamic forces, represented by the aerodynamic matrix, appear on the left-hand side of the equation, together with the internal system forces due to stiffness and inertia, represented by the stiffness matrix K and the mass matrix M. And the right-hand side of the equation is a zero vector. It is assumed that the displacement vector phi as a function of time can be written as a product of a time-independent vector phi hat, which contains the displacement amplitudes, and a scalar periodic time function. With this approach, the system of equations becomes time-independent. Such a homogeneous system of linear equations poses an eigenvalue problem, which is typical for the mathematical description of stability phenomena. The eigenvalues in this case are the circular frequencies of vibration of the structure, omega, which, for this kind of problem, result as complex quantities. The problem considered here is particular in that the aerodynamic forces, and hence the aerodynamic matrix A, depend on a non-stationarity parameter, the so-called reduced frequency k, which is yet to be determined. K is defined as a function of the circular frequency omega and the wind speed u, which are both unknown at the beginning of the computation, and the width of the bridge stack represented by b. Because there are two unknowns, circular frequency and reduced frequency k, a second condition is necessary. The flutter speed is a limit speed, similar to the buckling load of a column. It is associated with a borderline stable state of harmonic vibrations in which the vibration amplitude neither decreases nor increases. The decrease of the vibration amplitude in a certain mode of vibration I is described by the logarithmic decrement delta I, which in turn is related to the imaginary part, omega I double prime, of the corresponding eigenvalue, omega I. When the vibration is purely harmonic, that is, when the amplitude neither decreases nor increases, the logarithmic decrement is 0. Therefore, the second condition is that the imaginary part, omega I double prime, of any of the eigenvalues omega I is 0, because then also the logarithmic decrement delta I is 0. A two-step solution procedure can be used. The eigenvalue problem is solved for many different fixed values of k, leading to eigenvalues omega as functions of k. The eigenvalues can then be plotted against k, or equivalently, as done here for an example problem, against the reciprocal of k, which is called the reduced wind speed. The two lowest eigenvalues, omega 1 and omega 2, are shown here. They are generally complex quantities. In the top part of the diagram, the real parts, omega 1 prime and omega 2 prime of these two eigenvalues, are shown. They represent the respective circular frequencies of vibration. When the wind speed, and hence 1 over k, is 0, omega 1 prime is associated with the first mode of natural vertical vibration, and omega 2 prime with the first mode of natural torsional vibration. For non-zero values of wind speed and 1 over k, the vertical and torsional motion components are always coupled in the associated modes of aeroelastic vibration. In the bottom part of the diagram, the logarithmic decrements delta 1 and delta 2 are plotted, which are related to the imaginary parts, omega 1 double prime and omega 2 double prime of omega 1 and omega 2. Now remember that the second solution condition is that any of the logarithmic decrements delta I is 0, indicating the borderline stable state of harmonic vibration. We find here that delta 2 indeed becomes 0 at a certain value of 1 over k, or equivalently at a certain value of k. This k is called the critical k. For smaller values of 1 over k and wind speed, delta 2 is positive, that is, the vibration is damped and the vibration amplitude becomes smaller and smaller. For larger values of 1 over k and wind speed, delta 2 becomes negative, which corresponds to a divergent vibration in which the amplitude of vibration increases. Hence, the zero crossing of the delta 2 branch here indicates the borderline stable state of constant amplitude harmonic vibration, which we have defined as flutter. The corresponding value of omega 2 prime for this critical value of k is the flutter frequency. The flutter speed can now be computed from the definition of k from the previous slide, this one, which is rearranged for the wind speed u, and then the critical value of k and the associated value of omega 2 prime are inserted into this rearranged equation. The flutter speed is a property of the bridge. For the bridge to be safe, it must be ensured that the flutter speed is high enough, that is, higher than the highest wind speed ever expected at the bridge side. From this equation, we can draw two interesting conclusions. The flutter speed is the higher the frequency of flutter vibration. The frequency of flutter vibration, in turn, lies between the lowest natural frequencies of vertical and torsional vibration of the bridge. And these frequencies are the lower the longer the span of the bridge. Now we understand why flutter comes into play, especially when designing long span bridges. In fact, for very large spans, it becomes the all-dominating design criterion. The natural frequencies of the structure can be raised by making it stiffer. Therefore, the second conclusion from this equation is that the flutter speed can be raised, and so the safety of the bridge can be enhanced by increasing the stiffness. Unfortunately, increasing the stiffness is not so easy and comes at a cost. When cross-sectional dimensions are increased to make the structure stiffer, building material is added. This, however, also increases the mass of the system, which in turn tends to decrease its natural frequencies. To make things worse, the relationship between stiffness and natural frequency is overproportional. For doubling the frequency and the flutter speed, the stiffness needs to be increased by a factor of 4. Thus, the true challenge here is to raise the flutter speed without much increasing the cost. True to the motto, an engineer can do for a penny what a fool makes for a dime. Let's consider other possibilities for raising the flutter speed of a bridge. The so-called twin deck, proposed by Richardson in 1981, is a clever way of doing this. The pressure equalization between top and bottom sides of a bridge deck reduces flutter-inducing forces. It is a passive aerodynamic measure that has successfully been implemented in a few bridges. The cost is clearly less than the cost required for achieving the same flutter speed increase by increasing the stiffness of the system. However, there is some additional cost. The crossbeams that are needed to connect the individual decks are quite substantial structural elements. The additional cost is estimated at 10 to 15% of the cost of the bridge superstructure. Another idea is to use movable control surfaces or flaps, the motion of which is actively or passively controlled to produce aerodynamic forces that counteract the flutter-inducing forces. Such devices are effective in theory, but they have not been implemented to date in any actual bridge. They meet resistance due to reliability and maintenance concerns, given their dependence on energy supply, control hardware, and software, or at least, in the case of passively moved control surfaces, moving parts. Such concerns are understandable because the failure of such systems would jeopardize the safety of the bridge. Such concerns and resistance would not be warranted with respect to the eccentric wing flutter stabilizer, given that it is a passive device with no moving parts. In addition, the wings and their support structures can be very light structural elements compared to the crossbeams in the twin deck concept, so that they do not entail great additional cost. The wings are placed with lateral eccentricities, called AC, and with vertical offsets to avoid aerodynamic interference between the wings and the bridge deck. The flutter speed of the bridge is efficiently raised, provided sufficient eccentricity is provided. The main reason for this is the aerodynamic damping produced by the wings of the rotational motion of the bridge deck. Consider a rotational motion with a rotational velocity alpha dot. The vertical velocity of the wings, v, due to alpha dot is alpha dot times AC, the eccentricity of the wings. When we assume a constant rotational velocity alpha dot, and quasi-stationary flow, we can superimpose the vertical velocity v on the horizontal wind speed u, which leads to an apparent angle of attack phi. Phi is proportional to v, and hence proportional to alpha dot times ac. The apparent angle of attack results in lift forces on the wings that are proportional to phi and hence proportional to alpha dot times ac. These forces have a lever arm with respect to the bridge axis, which is the eccentricity ac. Consequently, they produce moments on the bridge deck that are proportional to alpha dot times ac square. Now consider that the viscous damping term in an equation of motion is governed by the velocity, in this case alpha dot. So the effect considered here corresponds to damping of the rotational motion of the bridge deck, and this damping is proportional to ac square, which means that the aerodynamic damping produced by the wings increases over proportionally with their eccentricity. The flutter speed of the bridge is raised by this additional damping. The more so, the greater the eccentricity of the wings. It is also of interest that both the leeward and the windward wing produce positive aerodynamic damping and thus raise the flutter speed. To verify the flutter suppression effectiveness of eccentric wings, we performed wind tunnel tests in our laboratory using a sectional model of the bridge deck without wings or with wings on either or both sides of the deck model, the latter case seen here. The model is spring supported so that the flutter speed can be measured directly. The table shows results for 4 selected test setups. The eccentricity and the width of the wings are always the same and corresponds to what could be seen on the previous slide. Only the wing arrangement differs. That is, these setups refer to arrangement without wings, with the wing on the windward side only, with wings on both sides, and with the wing on the lee side only. When a wing is absent, its mass is replaced by ballast so that the differences between the respective results only reflect the aerodynamic effect of the wings and not their mass. The 4th column of the table shows the flutter speed measured in the wind tunnel, and the next column the relative flutter speed increase compared to the no-wing situation, that is setup 1. The flutter speeds for these test setups were also analytically predicted using Theodorson's flutter theory. The results are shown in the next column, and the relative flutter speed increase, again compared to the no-wings situation, in the last column. The experimental and analytical results are in relatively good agreement, considering that a trapezoidal deck cross-section was used in the test, but a thin flat plate is assumed in Theodorson's theory. These results confirm that the flutter suppression effectiveness of eccentric wings exists, but also that this effect can be calculated with reasonable accuracy. The further results I'm going to present are all obtained by analysis. In a real-world application, it is economical to place the wings not over the entire length of the bridge, but only at regions where they are most effective, say at the center of the bridge main span, where the vibration amplitudes are large. In such a case, the torsional vibration mode component is changed by the wings and differs from the vertical mode component, which remains virtually unchanged. For this reason, it would be problematic to generalize such a configuration to just 2 degrees of freedom, heave, and rotation, as is normally done in flutter calculations for bridges and airfoils. To be able to accurately model such configurations, a finite element multi-degree of freedom flutter analysis method has been developed that is based on the finite aeroelastic beam element shown here. Because of the vertical offset between the wings and the bridge deck, it is assumed that there is no aerodynamic interference between these elements. Instead, the aerodynamic forces on both the deck and the two wings are separately described by the respective non-stationary aerodynamic coefficient functions, the so-called flutter derivatives, but summarized in one common aerodynamic element matrix. Taking into account the kinematic relationships between the displacements of the wings and the degrees of freedoms of the bridge deck. Mathematical representation as an eigenvalue problem and matrix notation and the two-step solution procedure for solving it are explained as before. It only needs to be added that the system matrices K, M, and A are assembled from the respective element matrices of the finite aeroelastic beam element of the previous slide. In addition, structural damping is now also taken into account. An elegant way of doing this is to use a damping parameter G, which represents damping as being proportional to the elastic restoring forces, but in counterphase to velocity. The latter is achieved by multiplying G by the imaginary unit I. The aerodynamic damping produced by the wings is included in the aerodynamic matrix A, together with the motion-induced aerodynamic forces on the bridge deck. With this method, a parametric study has been performed in which both the properties of the bridge and the configuration of the wings were varied. Instead of focusing on a particular long-span bridge type, a simple generic bridge system is considered, namely a simply supported girder with torsionally fixed ends. With respect to flutter, the properties of a bridge can now be summarized in a limited number of parameters, which are the two-dimensional quantities omega h and b, that is the lowest natural circular frequency of vertical vibration and the bridge deck half-widths, and four non-dimensional parameters, which are epsilon, the ratio of the first torsional and vertical natural frequencies of the bridge, mu, the structure to air mass ratio, r, the reduced mass radius of gyration, and g, the structural damping parameter. Concerning the wing arrangement, it is assumed in this study that identical wings are placed on both sides of the girder, that is, on its windward side and lee side. The wing configuration is then defined by four non-dimensional parameters: the relative wing eccentricity, AC tilde, and the relative wing width, BC tilde, both defined by relating the respective dimensional measures, AC and BC, to the bridge deck half-width B. The relative wing length, LC tilde, which is the length of one wing related to the length of the bridge, and the relative wing mass, MC tilde, which is the mass per unit length of one wing divided by the mass per unit length of the bridge deck. Also, the results are presented as non-dimensional quantities, namely the non-dimensional flutter speed, zeta, defined as a ratio of the flutter speed to the dimensional parameters of the bridge, omega h and b, and the flutter speed increase ratio r, that is, the flutter speed of a bridge with wings divided by the flutter speed of the same bridge without wings. It is of particular interest that the non-dimensional results, that is, the non-dimensional flutter speed and the flutter speed increase ratio, do not depend on the dimensional quantities, omega h and b, but only on the 2 × 4 = 8 non-dimensional input parameters that describe the bridge and the wings. A number of actual or planned long-span bridges were considered, and their respective parameters, epsilon, mu, and r, here highlighted in bold, were established. On this basis, the parameter space for the bridge systems to be studied was chosen. The parameter space for the wing configuration was chosen on the basis of previous studies of the flutter suppression effectiveness and the mass of the wings. The relative wing eccentricity AC tilde, for instance, was varied between 1 and 2.5. A value of 1 corresponds to wings placed directly above the edges of the bridge deck. Values greater than 1 correspond to wings positioned outboard the bridge deck. The relative wing length, LC tilde, was varied between 0 and 1. A value of 1 corresponds to wings placed along the entire length of the bridge, and a value of 0 corresponds to a bridge without wings. The results shown in the following were obtained with the flutter derivatives derived by Theodorson for a flat plate cross-section for representing the wind forces on the bridge deck and the wings. So these results apply to bridges with a streamlined bridge deck, such as a trapezoidal box girder, and to streamlined wings. Let me now present some of these results. The bridge system without wings is considered first. The diagram shows the non-dimensional flutter speed, zeta, of the undamped system plotted against the frequency ratio epsilon for selected values of the mass ratio mu and the mass radius of gyration r. The characteristics visible here are well known. In particular, the flutter speed always increases with the frequency ratio epsilon, with the exception of a small range of epsilon close to 1. Furthermore, there always exists a start value of epsilon below which no flutter occurs, and this start value is always larger than 1. We focus on two of these curves, namely the bottom one, established for mu equal 15 and r equal 0.7, and the top one for mu equals 60 and r equal 0.9. These two curves are reproduced on the next slide, which are this one and this one, together with other curves for other conditions. The two curves repeated from the previous slide are now labeled A, meaning no wings undamped. The two curves labeled B, this one and this one, result when structural damping is added. The flutter speed increases, although the differences between curves A and B become significant only for small epsilon, as seen here and here. Wings are now added on both sides of the bridge deck along the entire length of the girder. The relative wing eccentricity is 2. The relative wing width is 0.1. The curves labeled C, D, and E, these ones and these ones, result when the wings are added. They differ from one another with respect to the additional consideration of wing mass and structural damping. The curves labeled C, this one and this one, are obtained when neither structural damping nor the masses of the wings are taken into account, and the curves labeled E, this one and this one, result when both are taken into account. In comparison to curves A and B, curves C, D, and E are more rounded and shifted upwards and to the right, both for the lower values of mu and r, which brings us from here to there, and the higher values of mu and r, which brings us from here to there. Furthermore, the start value of epsilon, below which no flutter occurs, increases. All these effects are particularly pronounced for the lower values of the mass ratio mu. To better illustrate the effect of adding wings, we now consider ratios of the flutter speeds of the bridge with and without wings. This diagram shows the flutter speed increase ratio r plotted against the frequency ratio epsilon, again for selected values of the mass ratio mu and the mass radius of gyration r. The wing configuration is the same as on the previous slide. Both the structural damping and the wing mass have been elected in the analyses. It is seen that the flutter speed increase ratio increases inversely to the mass ratio mu for all values of epsilon. This kind of dependency can be ascribed to the force ratio of the aerodynamic damping forces produced by the wings to the internal system forces due to inertia and stiffness. The internal system forces become smaller and smaller for smaller mu, and thus the force ratio becomes smaller, which makes the wing-produced damping relatively more effective for smaller mu. It is also found that the flutter speed increase ratio always increases with increasing epsilon up to a certain start value of epsilon, below which no flutter occurs. Overall, we can conclude that a significant increase in flutter speed can be achieved by adding wings, particularly for the lower values of mass ratio and frequency ratio. In the next diagram, the flutter speed increase ratio is plotted against the relative wing eccentricity AC tilde, now for selected values of frequency ratio epsilon and mass ratio mu, the other parameters being set at fixed values. The flutter speed always increases over proportionally with AC tilde, which underlines the efficiency and usefulness of eccentricity. A relative eccentricity of 1 corresponds to wings placed directly above the edges of the bridge deck, as mentioned before. The flutter speed increase achieved with such a wing configuration is mostly small. Thus, it is generally worthwhile to provide a larger eccentricity of the wings than 1 and to position the wings outboard the bridge deck. Finally, the dependency of the flutter speed increase ratio on the relative wing length LC tilde is considered. For small epsilon and mu, the curves increase over proportionally with LC tilde. They end at a certain value of LC tilde above which no flutter occurs, even if not visible within the range of R shown here. For the other values of epsilon and mu, the curves show a more linear characteristic at first and then rise underproportionally, approaching their final value asymptotically at LC tilde equal 1. It can be read from the diagram that the flutter speed increase ratio of 64% is achieved with wings that extend over just 20% of the length of the bridge, in case of a frequency ratio of 1.3 and a mass ratio of 15. For this combination of parameters with LC tilde equals 0.2, I would like to present a detail of the multi-degree of freedom flutter analysis. In this diagram, the first 4 eigenvalues, omega 1 to omega 4, are plotted against the reciprocal of the reduced frequency, that is, the reduced wind speed. As before, the real parts, omega I prime, are shown at the top of the diagram. They represent the circular frequencies of vibration modes 1 to 4. At the bottom, the respective logarithmic decrements delta I are plotted, which are related to the imaginary parts, omega I double prime, of the eigenvalues omega I. At a certain critical value of the reduced wind speed, the delta 2 branch crosses the zero line. So, delta 2 and omega 2 double prime become 0 for this value of 1 over k. This value of the reduced wind speed, multiplied by the associated value of the flutter frequency, omega 2 prime, and the bridge deck half-width b, is the flutter speed, as explained before. The length of the wings is now increased from 20% to 32% of the length of the bridge, keeping everything else unchanged. To emphasize the differences, I'm switching back and forth between these two slides a few times. We see that the frequency branches remain virtually unchanged. The frequency branches remain virtually unchanged. A notable change, however, occurs in the damping branches. All 4 delta branches shift downwards to higher values. This is due to the higher aerodynamic damping provided by the longer wings. This downward shift causes the delta 2 branch to cross the zero line at a higher value of 1/k of the reduced wind speed, which in turn leads to a greater flutter speed, given that the flutter frequency remains virtually unchanged. When the wing length is further increased, the boundaries of the critical range, the range where delta 2 is negative, these 2 boundaries move towards each other, then merge into a point which finally disappears when this branch completely withdraws below the zero line. The merged point condition marks the wing length above which no flutter occurs. Giving the glancing intersection between the delta 2 branch and the zero line, a small additional increase in wing length is sufficient to reach this merged point and no flutter condition. The flutter mode shape for this combination of parameters is intrinsically complex. This representation refers only to the torsional component of the flutter mode shape. The flutter mode has been normalized so that the maximum value of its vertical component is 1. The vertical component is not shown in this representation. With the chosen normalization, it is almost completely real, that is non-complex, and an almost perfect sine half wave with a maximum value of 1 at midspan. Now the torsional component has both a real part and an imaginary part. The imaginary part resembles a sine half wave. The real part is strongly indented around midspan, an effect produced by the concentration of the wings at that location. This indentation, or rather the different forms of the real and imaginary parts, causes the argument of the complex torsional component to vary along the length of the bridge. This means that the phase shift of the torsional component relative to the vertical component is not constant, but varies along the bridge axis. These results support the earlier statement that with such a configuration, the vibration mode changes, and therefore it is more accurate to perform a multi-degree of freedom analysis instead of generalizing the system to just 2 degrees of freedom. We have seen that in certain cases, a significant increase in flutter speed can be achieved with wings that extend over just 20% of the bridge length. Design studies for such a wing configuration have been made, and it was found that the corresponding cost of the wings and their support structures is on the order of 1.3% of the cost of the bridge superstructure. This study has been done assuming a streamlined bridge deck. For non-streamlined decks, the achievable flutter speed increase ratio is larger at the same cost because the flutter speed without wings, in such a case, is lower, and therefore the wings are relatively more effective. The following conclusions can be drawn. The flutter speed of a bridge can be increased by lateral wings that are rigidly attached to the bridge deck. The flutter speed increases over proportionally with the eccentricity of the wings. The wings can be shorter than the bridge, which enhances cost efficiency and, incidentally, is a freedom of design not available in the twin deck concept. The wings are particularly cost efficient for light bridges with small torsional to vertical frequency ratio. Another interesting point is that the wings can produce a cost benefit also for smaller spans that normally do not require dedicated flutter suppression measures, because a more economical, non-streamlined and therefore prone to flutter bridge deck can be used, which is then stabilized against flutter by wings. Finally, because the wings produce damping, they also dampen vibrations due to other kinds of excitation. This concludes my presentation. I hope you have enjoyed it and perhaps have become curious about the device just presented. The parameter study with much more detail has recently appeared in the Journal of Wind Engineering and Industrial Aerodynamics. Here's also my email address. I would be happy to learn about your thoughts and read your comments or questions. Well, this finally really concludes my presentation. Thank you for listening. I look forward to hearing from you.